Welcome to Microwave Engineering lecture series. In this lecture, we will discuss about the line at zero dissipation and standing wave ratios. Line at zero dissipation is in this line. So let us consider the characteristics impedance equation. So this characteristic impedance and propagation constant, this all already we have discussed in a previous lecture series. So Z naught is equal to Z by Y. So this Z is R plus J omega L divided by G plus J omega C. This is the characteristic impedance, and for propagation constant is gamma is equal to root of Zy, which is equal to R plus J omega L into G plus J omega C. So we know this in high frequency this resistance and conductance will be very less. So this J omega L will be greater than R, and then J omega C will be the greater than G. So we assume this R and G will become 0. So Z naught is equal to J omega L divided by J omega C. So with J will get cancelled. So we get only the characteristic impedance is the real resistive, that is of root of L by C. Similarly for propagation constant gamma, that is gamma is equal to root of Z into Y, that is this will become as 0. So we get only the J omega L into J omega C. So J will get outside J square, that is J omega into root of LC. So this gamma is equal to 0 alpha plus J beta, that is this alpha will become as 0 plus J omega into root of LC. So the velocity of propagation is given by V is equal to omega by beta. Beta is equal to omega into root of LC. So from equation this is the velocity of propagation V is equal to C by F. We know this. So the line and corresponding shift from the signal of wavelength of 0 will vary from 0 to 2 pi. That is lambda is equal to 2 pi by beta. So we know this beta is equal to omega into root of LC. So this is a standing wave ratio. In a transmission line, if the load impedance is not equal to the characteristic impedance, that is ZR is not equal to Z naught, the energy delivered to the load is reflected back to the source. So the actual voltage at any point on a transmission line is the sum of the instant and the reflected voltage at that point. So the resultant total voltage wave appears to the stand, that is on a line and oscillating in a magnitude with time, having a fixed position of maximum and the fixed minimum. Such wave is called as a standing wave. So here you can see this graph. Here you can notice this is the standing wave for any dissipation less line. So this is the magnitude of the voltage which is standing from maximum, this is the voltage maximum, the maximum voltage minimum. So this is what the resultant total voltage wave appear, which is standing still on a line. So which is still on a line with the oscillating magnitude, which is having the fixed position. So we know this is the maximum point and this is the minimum point. So standing wave is nothing but voltage to the maximum to the minimum wave ratio. So there's so when it is happening is when your wave is traveling from one end to the other end. So it is in a distortion condition. So if you see this ZR, that is RR is not equal to R naught. That is when your line is not equal. That is in a dissipation line. So when the line is terminated with a load other than or not, then the voltage and the magnitude of the current measures along the line. So which you can see in the graph, that is when the standing wave line is happening on the open or a short circuited termination. If the line is either short circuit or the open circuit at the receiving, we have the nodes and the antinodes in the voltage distributions. The node or the point of zero voltage or current. The node or the point is already we have seen, this is the node and this is the antinode. So E and current and voltage will become a 0 in the standing wave points. So antinodes are the loop points or the point of the maximum voltage or the current. So the line is terminated with the R naught, has no standing wave ratio. If the line is terminated means that is it is a short circuited. So we don't have the nodes or the loops straight line, that is of smooth line for if the line is not terminated with the load or the source. For the open circuit, the voltage node occurs at the distance of lambda by 4, 3 lambda by 4 or the 5 lambda by 4 from the open end of the line. Under this condition, the current node occurs at the distance of 0, lambda by 2 and the 3 lambda by, that is of open termination. So for every distance, we have to see whether the line is open or closed. And for the short circuit, the node will be shifted for the every lambda by 4 condition. So voltage node occurs at 0, lambda by 2 lambda, and the current is, for you can see this, for every from starting point, it is current is moving to the up to the lambda by 4 condition. So we can observe this, the current, if this is the E maximum point, here it is the E maximum, this is the E maximum is the node, and then here when it is reaching, the E minimum is the antinode point. Do we the antinode? So standing wave ratio is the ratio of maximum to the minimum magnitude of the voltage and current on a line is having the standing wave ratio, that is denoted by S. So VSWR is equal to V max by V minimum, which is equal to the I max by I minimum. The maximum of voltage along the line occurs at the point when the incident and the deflector waves are in phase or either are directly. So this the maximum of voltage, see this is the voltage and the current, all both are in phase, and it has to be add directly, then only we get the standing voltage, will get maximum voltage and minimum at this point. This is the standing wave ratio equation. Similarly, we get this from the voltage and the current equation, that is V max and the V minimum. V is VR divided by 2 into zeta. This are the previously we have discussed this equation. Zeta plus or not into 1 plus mod K is the reflection coefficient. With respect to this, S will be the voltage maximum to the voltage minimum, which is equal to the 1 plus K, 1 plus reflection divided by the 1 minus K. So that is K and S will be the almost both are in directional proportional. So this S is equal to 1 plus K and K is equal to S minus 1 divided by S plus 1, where S is the standing wave ratio. So VSWR is the voltage standing wave ratio, that is V max by I max, and similarly current standing wave ratio is the I max by I minimum. So the standing wave ratio will be ranging from 1 to infinity, whereas the K will be ranging from 0 to 1. So with the standing wave ratio, S is equal to V max by V minimum. So we get this S is equal to 1 plus K divided by 1 minus K. So by V max minus V minimum divided by V max plus V minimum. So that is equal to this equation. So K is equal to S minus 1 divided by S plus 1, which is equal to V max minus V minimum divided by V max plus V minimum. This all we have to remember these equations for doing this calculations, and next upcoming lecture series we will discuss about the problems also. So thanks for watching. In next lecture we will discuss about the equator wave transformer.